Hello and good afternoon friends, welcome to CEC live lectures. Dear friends, today in this session we are going to continue with our series on natural products and spectroscopy. Today we are going to talk on ultraviolet spectroscopy. Dear friends, we are pleased to announce that we would be continuing with this particular topic in our forthcoming session also, though we'll try to cover the maximum part on ultraviolet spectroscopy today only. And for this discussion, we have once again with us in our studios Dr. Vandana. Dr. Vandana is an assistant professor in Department of Chemistry, Dal Singh College, University of Delhi. Dear friends, if you want to ask questions from Dr. Vandana on ultraviolet spectroscopy, then you can call right in the studio. You can contact us through our toll-free number. Our toll-free number is 1-800-110-430. I repeat, our toll-free number is 1-800-110-430. So let's welcome our guest, Dr. Vandana, and let's try to understand what ultraviolet spectroscopy is. Hello ma'am, welcome to the lecture.
Thank you so much ma'am. Hello viewers, we have started our series Natural Product and Spectroscopy. So why we are discussing this important topic is spectroscopy. You know, to analyze any organic compound we have classical methods. You have to go through the several steps, like first of all you need to identify the preliminary examinations for a particular organic compound, which includes the solubility, the liquid state or solid state, the solubility in water or in organic compounds, and the saturation and unsaturation of that particular compound. And second step, the detection of extra elements. Then third step is the detection of melting point or boiling point, then preparation of a derivative, and in the last the test for the melting point of that particular derivative. These were the classical methods to analyze a particular organic compound for the elucidation of a structure of an organic compound. And now we have an advanced technique, spectroscopy. Basically, what is a spectroscopy? It is an advanced technique to elucidate the structure of organic compound, to purify, to analyze whether the compound is pure or impure. So what is spectroscopy basically is? Spectroscopy is nothing but interaction of electromagnetic radiations. There are various electromagnetic radiations with organic compound. Like, we cannot identify the entire organic compound with a single test. We need to perform different tests to identify the different criteria. Like, if you want to identify the elements, you need to perform the different test. If you need to perform the functional group, you need to perform the different test. Same here. If you need to identify the entire structure of an organic compound, you need to go through the different types of spectroscopy. On the basis of electromagnetic radiation which interacts with the organic compound, spectroscopy can be different types, like ultraviolet spectroscopy, which include ultraviolet electromagnetic radiations interaction with organic compound, like IR spectroscopy, like NMR spectroscopy, which includes radio waves, like mass spectroscopy, like EPR spectroscopy. So there are various types of spectroscopic techniques which entirely elucidate the structure of an organic compound. So first of all, we need to understand what are electromagnetic radiations. What are the characteristic criteria of electromagnetic radiations? There are particular characteristic properties of electromagnetic radiation. First of all, it was believed that light travels in a straight line, but this concept could not explain some important phenomena. We know it, that is interference and refraction. Diffraction also. To explain these phenomena, light is exposed to travel in waves also, and in the form of energy. It can be explained by two complementary theories. We have studied corpuscular theory and wave theory. All the properties of light can be explained by considering both the theories, that is corpuscular theory and wave theory. According to wave theory, light travels in the form of waves. It was believed that radiant energy is emitted by fluctuation of electric charge and magnetic field. Like there are various forms of electromagnetic radiation such as ultraviolet, infrared, X-rays, radio waves, etc. Some of the important characteristics of electromagnetic radiations are, these are produced by the oscillation of electric charge and magnetic charge which resides on particular atom. the electric and magnetic components are mutually perpendicular to each other. You can see mutually perpendicular to each other, electric vector as well as magnetic vector. These are characterized by particular wavelength, frequency, or we can say wave number also. Another point, energy carried by electromagnetic radiation is directly proportional to its frequency, and the emission or absorption of radiation is quantized, and quantum of radiation is called a photon. All types of radiations travel with the same velocity and no medium is required for their propagation. They can travel through vacuum when there is no air. When visible light is passed through a prism, you have studied in 12th standard, it is splits into 7 colors, and this is called Vibgyor, correspond to definite wavelengths, and this phenomenon is called dispersion. Thus, a group of electromagnetic radiations can be split into various components for analysis. Now, what is the fundamental theory of spectroscopy? How spectroscopy works for the elucidation of organic compound? The study of spectroscopy deals with the emission as well as absorption spectra. Then what is emission spectra? It is nothing but produced by the emission of radiant energy by an excited atom. So you need to excite atom first by thermally or photochemically. The excitation of atoms can be brought about thermally, as we have stated, by heating the substance strongly, or electrically by passing the electric discharge through the vapors of the substance at a very low pressure. When electric discharge is passed through the vapors of the substance, energy is absorbed, and what happens? The electrons of an atom get excited from ground state to metastable states. When electrons from metastable state jump to the back, or we can say in lower energy state, then some energy of definite frequency is released as a radiation. If this radiation emitted is analyzed with the help of spectroscope, a spectrophotometer, an instrument that elucidates the structure or helps in elucidating the structure of organic compound, an emission spectrum is observed. If electromagnetic radiation of certain wavelength range are passed through the substance under analysis for substance, the wavelength which are absorbed characteristics some particular functional group present in the compound or the compound itself, this dark pattern of lines which correspond to the wavelength absorbed is called absorption spectrum. After absorption, the transmitted light is analyzed by the instrument spectrophotometer relative to the energy may heat up by the sample or re-emitted. Now, what is wavelength? We are talking about the characteristic property of electromagnetic radiation. It is the distance between the two adjacent crescent, carbon CC, troughs crest CC, or troughs TT in a particular wave, denoted by lambda, expressed in angstrom units or in millimicron, m mu. Visible light constitute wave ranging from 3800 to 7600 angstrom. This is called violet end and this is called red end. Human eye is sensitive only to small visible range and cannot detect ultraviolet light, that is wavelength lower than 3800 angstrom and infrared wavelength lower than 7600 angstrom. Ultraviolet light can be detected by photoelectric cell and infrared light can be detected photographically in some techniques like ultraviolet and IR spectroscopy. The common unit is wavelength. What is wave number? It is the reciprocal of wavelength. So it can express in per centimeter. In other words, it is defined as the total number of waves which can pass through in a space of 1 centimeter and expressed by nu bar, frequently used in IR technique, IR spectroscopy. If the wavelength of the light radiation is known, the corresponding wave number can be calculated as it is reciprocal of the wavelength. You can see what is the lambda. These two crests are here, so this distance is known as lambda, or we can say the distance between two troughs, it is also a lambda. If the wavelength of a radiation is 2.5, say mu, then the corresponding wave number can be calculated by the reciprocal of lambda. It will be, the wave number will be 4000 centimeter inverse. Now, another characteristic of a electromagnetic radiation, that is frequency. It is defined as the waves which can pass through a point in 1 second. Expressed in nu, in cycle per second, can be expressed, or in hertz, where 1 hertz is equal to 1 cycle per second. You can see the formula where you can see nu is the C divided by lambda. C is the velocity of electromagnetic radiation. This is nothing but 2.9 into 10 to the power 10 centimeter per second. So we know the wavelength range of visible range is 3800 angstrom to 7600 angstrom. Electromagnetic spectrum and absorption of radiations. The arrangement of all types of electromagnetic radiations in order of their increasing wavelength, or we can say decreasing frequency, is known as complete electromagnetic spectrum. The visible spectrum represents only a small portion of the electromagnetic spectrum. It starts from violet end to red end. If we arrange all types of electromagnetic radiations in order to of their increasing wavelength, then the above portion from the visible range is called IR, while that below it is called ultraviolet region. IR radiations have longer wavelength and are least energetic. Microwaves have larger wavelength and are used in telephone transmission. Here you can see the electromagnetic spectrum, and various electromagnetic radiations are here. First of all, you can see gamma rays, 10 to the power 0, wavelength, it is wavelength. Gamma rays, ultraviolet rays, you can see the small portion of visible range. And this is the angstrom value of wavelength, that is 3800 to 7600. This is 10 to the power 4 to 10 to the power 5, it is termed as near IR. 10 to the power 5 to 10 to the power 6 is called far IR. Microwaves and radio waves. You can see wavelength is increases and frequency is decreases. Although all types of radiations travel as waves with the same velocity, yet they differ from one another in certain properties. How they differ? X-rays, you know very much, can pass through glass and muscle tissues. Radio waves can pass through air. Visible ultraviolet and IR radiations can be bent by reflection or diffraction in a prism and so on. If some light radiation is passed through a sample of an organic compound, then some of the wavelength get absorbed while some get unaffected, or you can say revert back. A molecule can absorb radiation of certain frequency if there exists within a molecule an energy transition of magnitude delta E, which is equal to h nu. The difference in energy. It is found that when light radiations are passed through an organic compound, then electrons of the component atoms get excited. In addition, there is a change in the energy of vibrational energy as well as rotational energy, and that will be observed due to change in electronic, vibration and rotational energy levels, which is permissible. You cannot say that all vibration or rotational energy level get absorbed by a molecule. No, only IR active, only few frequencies or energies get absorbed by a molecule. It will be discussed in IR spectroscopy. The wavelength absorbed are measured with the help of a spectrometer, or we can say spectrophotometer. If we plot the changes in absorption against wavelength, we get certain absorption band which are highly characteristic of a compound. If the technique provides an excellent tool to ascertain the molecular structure of an unknown substance, or we can say we can identify the purity, or we can check the purity of a compound. Now, visible and ultraviolet radiations, which covers this range 200 to 800 millimicron. The absorption of radiation in this region causes the excitation of pi electron in a conjugated system, or in unconjugated system sigma electrons. The separation between the ground state and the excited energy level will be the less, and hence absorption occurs at a longer wavelength. Also, carbonyl group of an aldehyde or a ketone absorbs at some characteristic wavelength. So you can easily identify whether in a compound conjugation is there or unconjugation is there with the help of particular energy or particular wavelength or particular frequency. Thus, an ultraviolet or visible spectrum is quite useful for the detection of conjugation, for the detection of carbonyl group is there, and may not provide any information from remaining part of the molecule. You have to take help of the other part of a spectroscopy for other characteristic of a compound. like IR spectroscopy. What is IR radiations? Which cover the wavelength range from 0.8 to 2.4 mu constitute near IR region. From 15 to 25 micron it is phi IR region, and the most useful region for IR spectroscopy is from 12.5 to 15 micron. It is most useful. These radiations are of higher wavelength and are hence less energetic, and absorption of radiation by an organic compound in this region causes molecular vibrations. The changes in vibrational levels are accompanied by the changes in rotational levels. Thus, certain bands appear which characteristically absorb for the stretching vibrations. We will discuss in detail in IR what are stretching vibrations, but we just have a look. These are also spectroscopy technique which helps in elucidation of complete structure of an organic compound. The absorption at higher wavelength in the IR region are most characteristic of a compound and also help in distinguish one compound from another, although more useful than ultraviolet technique, because ultraviolet techniques only provides information about conjugation, non-conjugated, which type of transitions are there. But IR can explain that which kind of functional group present in the organic compound. So it is more useful than ultraviolet visible spectroscopy. The third type of spectroscopy is NMR spectroscopy, which provides a complete insight into the environment and the arrangement of atom. Which atoms? Proton. We are talking about the types of hydrogen atom. How many hydrogen atoms are there on a particular carbon atom, and which kind of hydrogen atom are there. For this technique, radiations of longest wavelength range, that is radio waves, are useful. For example, if we talk about CH3CH2OH, that carbon number 1, there are 3 hydrogen, carbon number 2, 2 hydrogen atom are there, and oxygen 1 hydrogen atom are there. So number of hydrogen atoms are different as well as their environment are also different. This we can elucidate by, or we can detect by NMR spectroscopy, nuclear magnetic resonance spectroscopy. We will discuss in detail in coming lectures. A sample under investigation is placed in a strong magnetic field and irradiated with radio waves. We are taking here which kind of electromagnetic radiations? Radio waves. Depending upon the strength of magnetic field employed, radiations of definite wavelength, or we can say in terms of frequency also, will be absorbed, which all bring the nuclear magnets into specific orientations with respect to the applied magnetic field. Due to different environment effect, different magnetic nuclei, for example nitrogen, carbon, fluorine, proton, with this particular number atoms can be used, which feel the applied magnetic field differently. We can detect these atoms in NMR spectroscopy, that what kind of nitrogen, carbon or fluorine or phosphorus atoms are there. Hence, absorption at different field strength will correspond to different sets of proton or magnetic nuclei. So we can easily find out the types of protons present in a particular organic molecule with the help of NMR spectroscopy or with the help of radio waves, electromagnetic radiations. So you are observing here that for a particular kind of characteristic of organic compound, we need to take the help of different type of spectroscopy. If you want to analyze the conjugation, non-conjugation or kind of excitation transitions in an organic compound, you need to take the help of ultraviolet spectroscopy. If you want to analyze which kind of functional group is there, you need to take the help of IR spectroscopy. If you want to analyze the kinds of protons or the relative environment of the protons, you need to take the help of NMR spectroscopy. From ultraviolet, IR, NMR, if we take the help of all three spectroscopy, you will be able to find out the structure of a particular organic compound. You can see the summary of these techniques. This is ultraviolet. You can see the range IR. This is the range of IR, radio waves, and electron beam impact, which includes in mass spectroscopy. The effect on molecule of a substance and in ultraviolet changes electronic energy levels within the molecule. You can easily analyze the conjugation, unsaturation, conjugation with non-bonding electrons, extent of pi electron system. We will discuss in detail in coming slides about this non-bonding electron, conjugation, unsaturation or extent of pi electron system. Now, if in IR spectroscopy, what you observe, the change in vibrational and rotational movements of the molecule and detection of almost all functional groups which have specific vibrational frequencies. For example, this is carbonyl group, this is hydroxyl group, this is amino group, this is acetylenic group, or etc. Any functional group you can analyze with the help of IR. Nuclear magnetic resonance, which include the radio waves, induce changes in the magnetic properties of certain nuclei. We have discussed in last slide, nitrogen, phosphorus also, notably that of hydrogen. Next, electron beam impact, which include changes in ionization, fragmentation of the molecule. If you want to analyze the molecular formula, the molecular mass of a compound, you need to take the help of mass spectroscopy, as well as if you need to analyze the fragmentation pattern or which kind of fragments or constitute inorganic compounds are there, you have to take the help of mass spectroscopy. Again, we will discuss in detail in coming lectures. And determination of molecular weight and deduction of molecular structure from the fragments obtained. Now, we are discussing in detail what is ultraviolet visible spectroscopy, what is the theory behind it. The alternate title for this technique is also called electronic spectroscopy, because we are discussing about the promotion of which kind of electrons are there, whether it is sigma, when sigma bond is there. If we talk about pi electrons, it means pi bond is there. If we talk about non-bonding electrons, it means non-bonding electrons are also there. From ground state to the higher energy state with the absorption of energy. When you follow electromagnetic radiation, let's say over here, ultraviolet visible electromagnetic radiation onto a organic molecule, it is very useful for measure the number of conjugated double bonds, also aromatic conjugation within the various molecules. It also distinguishes between conjugated, non-conjugated system, alpha beta unsaturated carbonyl compounds, beta gamma analogous homoannular, heteroannular conjugated dyes, etc. for visible and ultraviolet spectrum. Electronic excitation occur in this range. You can see the range of electronic excitation 200 to 800 millimicron, and involves the promotion of electrons to a higher energy molecular orbital. Since the energy levels of a molecules are quantized, the energy required to bring about excitation is a fixed quantity. Thus, the electromagnetic radiation with only a particular value of frequency will able to cause excitation. It is not there that all kind of energy will induce the excitation. Only a particular value of frequency will induce the excitation. Clearly, if molecule is exposed to radiation of some different value of frequency, energy will not be absorbed, thus light or radiation will not suffer any loss in intensity. Substance absorbing in the visible range will appear colored to the human eye. The wavelength of particular radiation absorbed can also be expressed in terms of energy, or we can say in kilocalorie per mole. You can see here this is mu, which is equal to 10 to the power minus 4 centimeter. So this you can see the units 1 millimicron is equal to 1 nanometer, or we can say 10 to the power minus 7 centimeter is equal to 10 angstrom. So we can calculate the energy associated with a particular wavelength. Let's say here if lambda is equal to 280 millimicron, then what will be the energy? You can see this will be the energy, because we are very much aware of this formula. E is equal to, if transitions are there, if electromagnetic radiations are fall on a molecule, so there is a change in the energy. Which kind of energy changes in a particular molecule depends upon the type of spectroscopy, and E is equal to, or we can say more precisely, delta E is equal to h nu, and nu is equal to, this is frequency C by lambda, or we can say frequency is the reciprocal of lambda. So here you can see the value of Planck's constant h, Avogadro number n, 6.023 into 10 to the power 23, or we can say in calorie also. So you can calculate the energy for a particular lambda for a particular frequency. Here you can see if in energy is higher side for a particular electromagnetic radiation, the frequency will also be higher and wavelength will be in lesser side. So you can characterize any electromagnetic radiation in terms of energy, in terms of frequency, in terms of lambda. A record of the amount of light absorbed by the sample as a function of wavelength of a light in millimicron or nanometer units is called absorption spectrum, which generally consists of absorption bands. The far UV region below 200 millimicron is not much studied. Why it is so? Because it is absorbed, this region itself is absorbed by oxygen and nitrogen. Moreover, studies in this region require vacuum instrument. This ultraviolet spectroscopy is governed by this the absorption laws, two absorption law. One is Lambert's law and another is Beer's law. What is Lambert's law? When a beam of monochromatic radiation, what is that? A radiation of a single wavelength passes through a homogeneous absorbing medium, it is proportional to the intensity of the incident radiation. For ultraviolet spectrum, the region starts from 200 millimicron to 380 millimicron. This is called quartz region also. And it is considered that molecular absorption in UV visible region depends mainly on the electronic structure of the molecule. Depending upon the presence of a common group or ultraviolet spectrum of a complex compound, that of a simple compound may be almost identical. What is Beer's law? When a beam of monochromatic radiation is passed through a solution of an absorbing substance, the rate of decrease of intensity of radiation with thickness of the absorbing medium is proportional to the intensity of not only incident radiation of incident light, but as well as the concentration of the solution also. So if you varies the concentration, the other things will also varies, or we can say rate of decrease of intensity will also varies. Now, what is a spectrophotometer? A spectrophotometer is a device which detects the percentage transmittance of light radiation when the light of certain intensity and we can say frequency range is passed through this sample. Thus, instrument compares the intensity of transmitted light with that of the incident light. Now, instrumentation, which includes how the instrument works for a particular spectroscopy. Here we are talking about the UV visible spectroscopy. The modern ultraviolet visible spectrophotometers consist of light source, monochromator, detector, amplifier and recording device. The suitable sources for lights are tungsten filament lamp, hydrogen deuterium discharge lamp, which cover the whole of the UV visible region. Tungsten filament lamp is particularly rich in red radiations, that is wavelength approximately 375 millimicron, while the deuterium discharge lamp covers the region below it. The single source is found satisfactory over the entire UV visible region. Ordinary spectrophotometer covers this range 220 to 800 millimicron. Better instruments cover up to a short wavelength range of 185 millimicron. This spectroscopic technique is not useful below 200. Why it is so? We have also stated that oxygen and itself absorb below this region. To study below 200 millimicron, the whole pan should be evacuated, that is, it should be free of oxygen. The region below is vacuum ultraviolet region and the low wavelength region can be extended up to 150 millimicron. Most spectrophotometers are double beam instruments, that is, beam need to be bifurcated. The primary source of light is divided first of all into two beams of equal intensity. Before dividing it into two beams, the incident radiation is dispersed with the help of prism, that it has to disperse in 7 colors. The various wavelengths of a light source are separated with the prism and then selected by slits, that we have to select a particular wavelength by a slits, such that the rotation of the prism causes a series of continuously increasing wavelength to pass through the slits for recording purposes. The selected beam now is monochromatic, because now we have first of all take the help of prism, and now we have a monochromatic radiation which is of single wavelength, which is then divided into two equal beam of equal intensity. Dispersion grating can also be employed to obtain the monochromatic beams of light from polychromatic radiation, that is from UV visible radiation. As the dispersion of a single beam or grating is very small, it is not possible to isolate very narrow bandwidths. Thus, light from the first dispersion is passed through a slit and then sent to the second dispersion for better dispersion, or we can say to have a particular wavelength or monochromatic light. After the second dispersion, light passes through the exit slit. The main advantage of second dispersion is that the bandwidth of emergent light increases and the light passing through the exit slit is almost monochromatic light. One of the beams of selected monochromatic light now is passed through the sample solution, and we have already stated that this monochromatic light is already bifurcated, and then other beam of equal intensity, you must note it through the reference solvent. The solvent as well as the solution of the sample may be contained in a cells made up of material which is transparent throughout the region. If it is absorbed itself, then how can you deduce the structure of a particular organic compound? It will interfere in the structure of organic compound. So you have to take the material which is transparent, should be transparent throughout the UV visible region particularly. Glass cannot be used because it absorbs strongly itself in ultraviolet region. So what can be used? Silica cells can be used. These must be properly stored and their optical surfaces should never handled by carelessly, or we can say with hands. Quartz cells also serve the purpose best. In the visible region, this type of spectrophotometer is called double beam spectrophotometer. Each absorption measurement on the solution is accompanied by simultaneous measurement of the pure solvent. Here you can see the instrumentation for UV visible spectrophotometer. This is the light source, and you can see here it contains radiation contains the polychromatic light, that different wavelengths are there. Now we are using this prism for dispersion. This is a rotating prism. What it does, it disperses the polychromatic light. Here you can see the slits, double slits are there, so that a monochromatic light should be here. Now this monochromatic light is divided into two. You can see here this is the sample light and this is the reference light, or here you can see the photocells P1 and P2. This is optical wedge. After electronic amplifier, it is coupled with motor and pen driver. Here you can see you will get the spectrum with pen recorder. Usually samples are scanned in dilute solutions. 1 milligram of the compound under investigation is accurately weighed and dissolved in suitable solvent to make the solution up to 100 ml volume. A little of this solution is taken in a silica cell. The thickness of the solution in this cell should be 1 centimeter. When the constituting the absorbing material is unknown, the absorptivity may be expressed in terms of E, 1 centimeter, 1%. Pure solvent is also taken in an exactly similar cell, or we can say reference cell, and these cells are then exposed to the monochromatic beams of equal intensity in the spectrophotometer after the beam passed through the sample cell as well as from the reference cell. The intensities of the respective transmitted beams are then compared over the whole length of the instrument. The spectrophotometer electrically subtract itself the absorption of the solvent in the reference beam from the absorption of the solution. Clean cell should be used because impure compound is there. So rinse with many times with the solvent to remove the last trace of the previous sample. Cell may be cleaned with the hot nitric acid or with a detergent. The absorption or transmittance characteristic of the compound alone can be measured. The singular for the intensity of absorption versus corresponding wavelength is automatically recorded on the graph, and this spectrum is usually plotted as absorbance, that is you can see here, and against wavelength, or the plot is often represented by E maxima, that is extinction coefficient, against wavelength. So you have studied about the general what is spectroscopy, why we are using this technique to elucidation of the structure of the organic compound, and we have studied the fundamentals of UV visible spectroscopy, and we have also studied the instrumentation or the instrument part of the UV visible spectroscopy. Hope you understood this part of the UV visible spectroscopy. Thank you. Hello viewers, we were talking about the UV visible spectroscopy, the fundamentals of ultraviolet spectroscopy. We have studied about the instrumentation. Now we are talking about the absorption bands, how they formed. We expect that spectrum of a consists of a sharp peak, and each peak will be corresponding to the promotion of electron from ground state to another state, that is metastable state. But actually sharp peaks are seldom observed. We observe the broad absorption bands. It is due to the fact that excitation of electrons are also accompanied by constant vibratory and rotatory motion of the molecules. The vibratory and rotatory modes are also quantized. Clearly, a molecule in a particular electronic state is also quantized. A molecule, normally the absorption of UV visible light results in single ground state to excited singlet state. That is, excitation proceeds with the retention of spins. The difference between two adjacent electronic levels is more as compared to the adjacent vibrational rotational levels, while the difference between the adjacent vibration levels has some intermediate value, and the electronic excitation is superimposed upon rotational as well as vibrational levels. During promotion, electron moves from a given vibrational and rotational level with an electronic mode. So you are very much aware that if a molecule is there, there are definitely vibrational motion as well as rotational motions are there, and corresponding energies are also there. Thus there will be a large number of possible transitions responsible for change in electronic, rotational and vibrational levels. Hence not just one but a large number of wavelengths which are close enough will be absorbed, resulting in the formation of broad band, not a sharp band. In more complex molecule which contain a large number of atoms, the multiplicity of the vibration sublevels and their closeness result in broad bands. More broad bands will be observed in that case. What is the theory of electronic spectroscopy, or let's say UV visible spectroscopy? When a molecule absorbs UV visible range, its electrons get promoted from lower state, or we can say from ground state to higher energy state. In the ground state, we know that atoms contain electrons, and the spin of the electrons in each molecular orbital are essentially paired in ground state. And in higher state, if the spins of the molecules are paired, it is called singlet state. If it is parallel, then it is triplet state. If triplet state is always lower in energy, why it is so? Because of the electrons. Corresponding excited singlet state, because parallel electrons are there, while in singlet state paired electrons are there. Therefore, triplet state is more stable as compared to the excited singlet state. In the triplet excited state, electrons are further apart in space, and thus electron repulsion is minimized and lower energy. The excited singlet state is converted to excited triplet state with the emission of energy, or we can say as light. The transition state from singlet ground state to excited triplet state is symmetry forbidden because the spins get change of electrons from singlet to triplet state. The higher energy states are designated as high energy molecular orbitals and also called anti-bonding orbitals. The highly probable transition due to absorption of quantized energy involves the promotion of electron from highest occupied molecular orbital, or let's say HOMO, to the lowest available unfilled molecular orbital, LUMO. In most of the cases, several transitions occur, resulting in the formation of several bands. So there are several types of electronic transitions because of different types of electrons involved in bond formation in a molecule. According to the molecular orbital theory, when a molecule is excited by absorption of energy, UV visible energy, its electrons get promoted from a bonding to an anti-bonding orbital. The anti-bonding orbital, which is associated with the excitation of sigma electron, is called sigma star anti-bonding orbital. So sigma to sigma star transition takes place when sigma electrons get promoted from bonding to anti-bonding, or we can say from ground state to excited state. It is represented by this way. You can see sigma arrow, sigma star transition. When a non-bonding electrons gets promoted to an anti-bonding sigma orbital, then it is represented by non-bonding to sigma star. Similarly, when pi bonds get promoted from ground state to excited state, this transition will represented by pi to pi star transitions because of the promotion of pi electrons to an anti-bonding pi star orbital. Here you can see the electronic excitation energy. If we talk about any molecule, it can contain sigma electron. It can, let's say CH3, CH3 or ethane, it will contains only sigma electrons. So only sigma to sigma star excitation of energy is there, we can say transitions are there. If we talk about CH3, CH2OH, ethanol, then along with sigma electrons, non-bonding electrons are also there on oxygen atom. So first transition is sigma to sigma star, another one is non-bonding to sigma star. If we talk about ethylene, CH2, CH2, then pi to pi star transition will be there, only pi to pi star and sigma to sigma star, because one sigma bond is there and one pi bond is there. If we talk about any molecule, let's say benzaldehyde, then non-bonding to pi star also observed there. Here you can see the energy difference also. From sigma to sigma star, this difference is largest because sigma bond is the strongest bonded among all. And here you can see when we talk about non-bonding to sigma star, the energy is less than sigma to sigma star but more than pi to pi star and non-bonding to pi star. And when we talk about this pi to pi star, here the energy difference will be less than the sigma to sigma star and non-bonding to sigma star, or we can say the energy is higher, the difference in energy, the transition energy will be higher with respect to non-bonding to pi star, or we can say the energy difference is the least in case of non-bonding to pi star. So you can see the order of transitions in terms of energy. For energy will be highest for sigma to sigma star, then non-bonding to sigma star, then pi to pi star, and then non-bonding to pi star. We can also make a order not only for in terms of energy, but we can in terms of frequency also, and for in terms of wavelength, the order will be reversed, because E is equal to, we can see the relation delta E is equal to Hc by lambda. Here also you can see the energy transitions. Various transition involved in UV visible spectroscopy. It is the high energy process, we have already stated, because the sigma bond is strongest. The organic compound in which all the valence shell electrons are involved in the formation of sigma bond do not show absorption in the normal ultraviolet region, that is 180 to 400 millimicron. For saturated hydrocarbons like methane, propane, etc., absorption occurs nearly. It is of highest energy, we have already stated, we have already discussed it. at 150 millimicron. Let's say consider this saturated hydrocarbon. You can see the transition from sigma to sigma start, from bonding sigma to anti-bonding sigma start, as all sigma bonds are there, no pi bond is there. Here you can see, if you see this carbon, single bond carbon, it will contain sigma to sigma start transitions, so energy difference will be highest. If we talk about carbon double bond carbon, you can see the type of transition pi to pi star. If we talk about carbonyl group, or we can say carbon double bond oxygen, so not only this sigma to sigma start, but we also observe this pi to pi star as well as non-bonding to pi star also. And you can see the difference of energy for particular cases. Such a transition requires radiation of very short wavelength. The usual spectroscopic technique cannot use below 200 since oxygen begins to absorb strongly. To study such higher energy transitions, or we can say below 200 millimicron in terms of wavelength, the entire path must be evacuated. Thus the region is called vacuum ultraviolet region. The excitation of sigma bond electrons to sigma starred anti-bonding orbital level occurs with net retention of electronic spin. It is called excited singlet state, which may in turn get converted to excited triplet state where the spins of the electrons are parallel. This region is less informative. Another transition is here, non-bonding to sigma star. This type of transition takes place in saturated compounds which also contain one heteroatom with unshared pair of electrons, that is non-bonding electrons. Some examples are here. You can see saturated halides, alcohols, ethers, aldehydes, ketones, amines. All they are saturated compounds along with heteroatom. Such transitions require comparatively less energy as compared to sigma star. For example, you can see water absorbs at 167, methyl alcohol 174 and methyl chloride at 169 millimicron. In saturated alkyl halides, the energy required for such a transition decreases with increase in size of the halogen atom. Why it is so? Because electronegativity decreases as the size increases. So here you can see this is carbon, saturated carbon along with the heteroatom which contains non-bonding electrons. So a non-bonding to pi star transition will include in this spectroscopy. Air must be excluded so as to avoid absorption due to oxygen. Let us compare non-bonding to sigma star transition in methyl chloride and methyl iodide. Due to greater electronegativity of chlorine atom, the pi electrons on chlorine atoms are comparatively difficult to excite. Here you can correct this. This is non-bonding electron, not pi electrons. The absorption maximum for methyl chloride is 172 to 175 millimicron, whereas that for methyl iodide it is 258 millimicron. As non-bonding electrons on iodine atoms are loosely bound, or we can say lower electronegativity. Since this transition is most probable in case of methyl iodide, its molar extinction coefficient is also higher compared to methyl chloride. Similarly, in case of amines, it will be absorbed at higher wavelength as compared to the alcohols, and hence extinction coefficient for amines will be higher. Non-bonding to sigma star transitions are very sensitive to hydrogen bonding. Alcohol as well as amines from hydrogen bonding with the solvent molecules. Such association occurs due to the presence of non-bonding electrons on the heteroatom, and thus transition requires greater energy. Hydrogen bonding shifts the UV visible absorption to shorter wavelength. Another transition is here, pi to pi star. This type of transition occurs in the unsaturated molecules. For example, when the compound contains double or triple bond, or in case of aromatic compound also. The excitation of pi electrons requires smaller energy. Hence, transition of this type occurs at higher wavelength. A pi electron of a double bond is excited to a pi star, or we can say pi star anti-bonding orbital. For example, alkenes, alkynes, carbonyl compounds, cyanides, azo compounds, etc. shows pi to pi star transition. You can see here the structural representation also. Here carbon, double bond, carbon. 4 electrons are there. First bond will be sigma, another bond will be pi. So pi to pi star transition it shows over here, because electrons get promoted from ground state to excited state. This transition requires still lesser energy as compared to non-bonding to sigma star, or let's say sigma to sigma star. Therefore, absorption usually occurs within the region of ordinary ultraviolet spectrophotometer. In conjugated alkenes, absorption bands appear near 170 to 190 millimicron. In carbonyl compound, the band due to pi star transition appears around 180 millimicron and is most intense, that is the value of extinction coefficient will be higher. The introduction of alkyl group to olefinic linkage produces a bathochromic shift. Now we are talking about this shift, whether the wavelength of a particular absorbed by a particular part of a molecule gets changed. Yes, it can definitely change by the introduction of alkyl group. Bathochromic shift, the shifts depend upon the type of alkyl group and the stereochemistry about the double bond. We will discuss in detail about the shifts due to the change in lambda or extinction coefficient. Another transition is here, non-bonding to pi star anti-bonding transition. In this type of transition, an electron of unshared pair electron on heteroatom get excited to pi star. This type of transition requires least amount of energy. All the transition discussed above are hence occur at longer, or we can say longest wavelength among all transitions. Saturated aldehyde have both the types of transition, that is low energy. It is comparatively difficult to promote electron from a lower energy level to higher energy level in this particular transition as compared to the other transitions, because the energy difference is least in this case. Greater the probability of a particular transition, greater value of its molar extinction coefficient. So E maximum shift towards longer wavelength. Pi to pi star and higher energy occurred around 290 millimicron and 180 respectively. Molar absorption occurring at lower wavelength is usually intense. In simple cases, it is quite easy to tell whether the transition is non-bonding to pi star or pi to pi star, since the extinction coefficient for the former is low as compared to that of the later, that is pi to pi star. The exact electronic structure of molecule in excited state by the absorption of UV, ultraviolet or visible light is not known, but the electronic transition involves redistribution of electrons within the molecule. In carbonyl compounds, a high energy non-bonding to sigma star transition also occurs and is quite intense. So you can easily analyze the carbonyl compounds with the help of these transitions. And two types of transition take place over here in saturated carbonyl compounds. That is higher energy transition when non-bonding to sigma star, the peak will be intense. Pi to pi star, again the high energy transition and the peak will be intense. Low energy transition, non-bonding to pi star, and you can also say it R band. In carbonyl compounds, the shifts in the absorption depends upon the polarity of the solvent. Now another term is here, transition probability. What is that? It is not always necessary that the excitation of an electron takes place from a bonding orbital or lone pair of two anti-bonding or non-bonding orbital when a compound is exposed to UV light. So here you can say what is extinction coefficient? It is nothing but E maximum is 0.87 into 10 to the power 20 Pa. What is P? It is the transition probability with values 0 to 1. And what is A? It is multiplied by A also. You can see this is the target area of the absorbing system, usually called a chromophore, and has a length of the order 10 angstrom to 10 to the power minus 7 centimeter. The chromophore with low transition probability will have E maximum value below 1000. there is a direct relationship between the area of chromophore, that is A, and the absorption intensity E maximum. In addition, there are some other factors also which govern the transition probability. Depending upon the symmetry and the value of E maximum, transition can be classified as allowed transitions and forbidden transitions. The transition with the value of E maximum more than 10 to the power 4 are called allowed transition. They arise generally due to pi to pi star transitions. For example, in butadiene, 1,3-butadiene, the absorption at 217 millimicron, E maximum is 21,000, that is 21,000, is an example of allowed transition. Chromophore is an isolated covalently bonded group which is attached to the group and shows a characteristic absorption in the ultraviolet visible region. The forbidden transition is a result of excitation of an electron from the lone pair present on the heteroatom to an anti-bonding pi star orbital, non-bonding to pi star transition near 300 millimicron in case of carbonyl compound, and the E maximum values varies 10 to 100. So because of this particular low value or because of this anti-bonding value, this transition will be forbidden in nature. The value of E maximum for forbidden transitions are generally below 10 to the power 4. Consider benzophenone. Here you can see the transitions value 252 millimicron and 325 millimicron wavelength, and E maximum for particular is 20,000. If it is 20,000 or above 10 to the power 4, it will be a allowed transition. If it is below, you can see the value E maximum is 180. So this transition will be forbidden in nature. Symmetry restriction in electronic transition. The transition is related with the geometries and the higher energy molecular orbital and also on the symmetry of the molecule. Symmetric molecules have more restrictions on their electronic transitions than less symmetric molecules. For example, benzene is a highly symmetric molecule. Thus, many restrictions apply to the electronic transitions of the benzene molecule, and thus its electron absorption spectrum will be simple. For a totally unsymmetrical molecule, or we can say no symmetry restriction apply to the electronic transition, so transition may be observed among all its molecular orbital except among filled orbitals. For such substances, a complex electronic absorption spectrum will be result. Between symmetrical and totally unsymmetrical extremes, a large number of organic compounds fall which absorb light in the UV visible region. To decide whether the transition is allowed or forbidden, we have to take these 3 points: the geometry of the molecular orbital in ground state, the geometry in excited state, and the orientation of the electronic dipole of the incident light and the might induce the transition. So the transition will be an allowed if the above 3 factors have an appropriate symmetry relationship. Now what is chromophore? All those compounds which absorbs light of wavelength between 400 to 800 appear colored to the human eye. You can see from naked eye. Exact color depends upon the particular wavelength absorbed by the molecule, and a chromophore was considered any system which is responsible for imparting color to the compound. For example, if you see nitro compound, these are yellow in color because of nitro group. This is chromophore. Clearly, nitro group is the chromophore which imparts yellow color. Similarly, aryl conjugated azo compound is a chromophore for providing colors to azo dyes. So we can understand what is chromophore. So today's lecture was based on ultraviolet visible spectroscopy, and why we are studying spectroscopy. Spectroscopy we have studied. In summary, we can say that spectroscopy is nothing but an advanced technique to analyze the structure of an organic compound, and you can easily identify the particular organic compound. If you are given a non-organic compound, how will you analyze? You can analyze with classical methods as you have studying in your undergraduate courses. The points were preliminary test, then functional group, extra element detection, melting point, derivative formation, and the melting point of that particular derivative. But advanced technique includes the spectroscopic techniques, which includes the different types of spectroscopy. For conjugation, for non-conjugation, you can take the help of ultraviolet is visible spectroscopy. For the detection of particular function group, you can take the help of IR spectroscopy. For kind of protons or number of protons in a molecule, you can take the help of NMR spectroscopy. For molecular weight determination, you can take the help of mass spectroscopy. So today we have discussed about the UV visible spectroscopy. In forthcoming lecture, we will discuss about the remaining portion of UV visible spectroscopy. Hope you understood this lecture. Thank you so much.
With this note, thank you, ma'am. Thank you so very much for your precious inputs to the lecture. Friends, your inputs are very, very important for us. Give your suggestion, feedbacks, or ask a question, because we want you to be in our contact continuously. For that, do write to us at info.cec@nic.in. We would be meeting again soon and would be continuing our series further. Till then, take care. Goodbye. Thank you, ma'am. Thank you once again.
Thank you so much.